We're just going to jump right back in. We were talking about performance, specifically range, and a little bit about endurance. We're going to talk about a few more performance aspects relating to climb and descent and turning. So first, descending. This is a scenario that's a little bit simpler than climbing, where the engines are off and we just want to see how far we could glide, right? And so we often talk about this in terms of a glide ratio. And the glide ratio is just, let's say this is forward distance relative to descent distance. Okay, so in other words, a glide ratio of 2 would mean that for every meter I dropped, I was able to go forward 2 meters. And you know, ideally I would like to have a high glide ratio. That's going to give me more options. If I had a scenario where I had you know, some engines out and I needed to land, I have more options available to me because I can go further, right? I can potentially go further if I have a higher glide ratio. We'd like to understand how to predict this, what performance parameters on the airplane dictate the glide ratio. The other related quantity is this angle here, gamma, which we call the glide path angle. So either glide ratio or glide path angle, they're going to be related. Okay, so, well, actually, let's write down specifically how they're related. If I look at this angle here, gamma, how is that related to the glide ratio? Well, we could see we could draw arbitrarily some location, right, and make a right angle. The tangent of gamma is this descent distance relative to the forward distance. So we could say this is 1 over the tangent of gamma, right? So it's forward distance, how far I go forward relative to how much I descend, right? Because we're assuming we're descending on this constant glide path angle, right? Just descending, constant angle all the way down. So I should draw this way, the way you're looking at it. All right, so just 1 over tangent of gamma. So now we want to relate that to the aircraft. What's happening at the aircraft? What are the forces on the aircraft? Well, we said the propulsion system is off. This is not a powered descent, it's just a glide. So no thrust, but we do have weight, and of course we do have lift and drag. So weight, of course, is always going to act down. So weight acts like this. And because I'm descending along this angle, then we know V infinity is in that direction, right? Because it's just relative to the motion of my aircraft. So by definition, drag is going to be along that direction and lift will be perpendicular to it. We also know just from the geometry of this, right? Since drag is aligned with V infinity, that means that this angle here, that's gamma, right? And this angle here is gamma. Those have to be the same angles, right? Because it's perpendicular to that curve. So we could write, if we just wanted to resolve forces, say we're doing a steady descent. The sum of the forces in the y is equal to 0. So we could say that we could say the lift, actually, we're going to do it. I'm just trying to think about which way we want to do it. It's going to be easier actually if I do it this way. Instead of doing this x and y, let's use, let's draw a line here, right? Let's use this coordinate system, this x and this y. And I obviously did a horrible drawing those perpendicular. Let's redo these a little bit. Okay, so drag is that way. Lift is perpendicular, right? So this is a right angle. This is gamma. This is gamma. Okay, so I'm going to do it along those tilted axes. It'll just be more convenient. So lift is going to be, has no drag component, right? Because it's perpendicular. So along this axis here, I've got a component of weight. That's going to be W cosine gamma. And then along this axis here, I've got drag is equal to W sine theta. Right, assuming I've got steady flight. So if I divide those, then I can see that L over D, lift over drag, is just equal to 1 over tangent of gamma. That shouldn't be surprising. We could actually have gotten this simpler without worrying about the weight, just because we know that lift and drag is perpendicular to gamma. Right, so if I could have written, I could have drawn the drag up here. I could have moved it up here, right? And I had this angle here. So the tangent of gamma is just going to be, well, d over L, right? The tangent of gamma is going to be this distance d divided by this distance L. All right, so let me just draw that a little clearer. I could have said, here's lift, here's drag. This is a right angle. All right, so gamma is this ratio d over L. Okay, so I'll just get rid of that. But we just did that a little more carefully, I guess. So what does that tell us? Our glide ratio is just equal to L over D, our lift to drag ratio. So it's purely aerodynamic, which of course it can't depend on the propulsion system. Propulsion system's off. It doesn't depend on the weight though, which may be somewhat surprising at first glance. Doesn't matter how heavy or light the airplane is, the glide ratio is going to be the same for a given L over D. So this is a purely aerodynamic phenomenon. If I have, let's say, an L over D of 20, and I start at 1,000 meters elevation, that means I could glide potentially 20,000 meters. And by the way, that corresponds to, say, 1 over, if I solve for this angle instead, that gives me 2.9 degrees, arctangent of 1 over 20. So fairly straightforward, right? If we know L over D, we can quickly figure out our glide ratio, or how far we're going to be able to fly starting at a given elevation. Okay, so let's now talk about a related problem. That's climbing or the rate of climb. How fast can I climb? So here's my airplane. It's climbing at this angle gamma, constant angle gamma. And now I want to do the same kind of analysis and figure out what are the forces that are acting on the vehicle. And instead of looking at how I'm descending, I'm going to look at how I'm climbing. So let's draw those forces again. Same as before. Weight is always down. Drag is going to be aligned with my free stream. Lift is going to be perpendicular to my free stream. And now the only additional force I have is I've got thrust, right? As I'm climbing, my propulsion system has got to be on. So I've got thrust. And I'm going to sum forces. And similarly, I'm going to do it like we did last time. I'm going to do it along, again, I did a bad job drawing perpendicular lines here. More like that, okay? So I'm going to do it along this axis and this axis. And we can see from the geometry that this angle here is going to be gamma. Okay, so if I do it along first, let's just do it along this axis here. I've got thrust and drag, and then I've got a component of the weight, W sine gamma. So I've got thrust, assuming a steady climb, equals drag plus W sine gamma, right? So it's balanced by this drag, and then this component of the weight right here. And then in that vertical relative to my airplane direction, the lift is going to be balanced by this component of the weight, W cosine gamma. Okay, so lift is equal to W cosine gamma, right? Okay, so that's my force balance for steady flight, and I want to figure out how fast I can climb. So how do I relate that? How fast do I climb? This isn't an angle, this is fast I'm climbing is a speed, right? So if I have this angle here, here's gamma, right? This is how high I'm going per unit time. What I want is h dot, meaning how fast am I going in the vertical direction? I know how I'm going this direction, right? This is my speed. I'm going that direction with speed v, but how fast am I going in the vertical direction? So if this is v, then h dot is just going to be the component in the vertical direction, v sine gamma. That's how fast I'm going up, right? So if I'm going forward, I'm going along the flight path of v, I've got a component of the velocity going horizontal and a component going vertical. So that vertical component we're calling h dot. It's v sine gamma. So I can now use this and substitute it in, or solve this for sine gamma. Actually, I guess I should draw the arrow the other way. I'm going to solve this equation here for sine gamma. Plug it in, and I get that my climb rate is going to be v times thrust minus drag over weight. Okay, so that's how fast I can climb. or my rate of climb as it's called. I guess I wrote h dot, but we typically call this rate of climb. So this equation helps us understand a few things. One is that remember for a jet-powered aircraft, last time we said that the thrust is relatively constant. So for jet aircraft, you'll often hear this ratio, thrust to weight ratio. When they're talking about propulsion systems, they'll often size it based on thrust to weight. And that's because that's directly related to my ability to climb. Right? If that thrust to weight ratio isn't big enough, it's not going to be able to climb. So that's important. For electric powered aircraft, the thrust is not constant, but the power is rather constant. And so this quantity here is my input power, right? The force times the velocity, that's power. That's going to be constant. So we talk about power to weight ratio. And you'll remember as we've been designing our electric powered aircraft, we've been talking about guidance on what's a good power to weight ratio. Thrust to weight is less relevant, right? Because thrust varies a lot, but the power to weight is more relevant. So again, that's related to our ability to climb. As an aside, remember last time we talked about the speed for maximum endurance, speed for max L over D, speed for max range, for example. There is also a speed for best rate of climb. For jet-powered aircraft, it is faster than the speed for minimum drag. So our max L over D speed would be flying actually a bit faster. For electric powered aircraft, because the power doesn't vary, it's the speed. Our best climb speed is our minimum power speed. Right? So that's going to be the maximum rate of climb speed, whatever minimizes power. That's a bit of a side. We're not going to really worry about that too much, but just to note that it is, again, another speed, right? A different speed to maximize this quantity. All right, so we talked about descending. We've talked about climbing. Last thing we're talking about today is turning. Okay, so we're going to do the same kind of thing. We're going to do another force balance, look at the forces that are acting on the airplane, and try to understand turning performance, what affects turning performance. So if we draw the forces, I've already drawn it with some turn here, and this turn here, phi is called the bank angle. I really should have drawn it this way because this airplane has some dihedral. Phi is really relative to, say, this reference line here. Oh boy, that's bad. Erase that, try again. Somewhere like this. Yeah, imagine that was a straight line. So phi is really relative to that rather than what I've drawn because that airplane has some dihedral. This angle here then is just going to be that dihedral angle. Okay, but that's not going to matter too much. We're not worried about that here. So phi is the bank angle. I've got the weight of the airplane, like before, and I've got lift and drag. I do have too, but that's going to be in and out of the page. That's not going to really enter into this analysis here. And I've already drawn the lift. You can see that it's tilted because I've banked the airplane. So I've got a component vertical, and I've got a component to the side. So from our force balance, assuming we're doing a steady turn, I need, or at least well, it's still going to be accelerating, but let's say we're at an equilibrium here vertically. I want to have this component of my lift balance my weight. Otherwise, I'm going to be dropping, right? Or I guess potentially climbing. But I want to have a steady turn where I'm not climbing or descending. So I want my weight, or I want this component of the lift, L times the cosine of my bank angle to equal my weight, which is mg, right? Okay, now I've got this component of my lift that's going towards the center. I've drawn it also here. We're turning, and so we're going to turn around some radius, and this is a centripetal force. So recall again, what do I want that centripetal force equal to? L sine phi is this component here. This is L sine phi, right? This is L cosine phi. So that's going to be mv squared over r, if we remember from physics. So that's the mass of an airplane times the speed squared divided by this turning radius r. Okay. Well, I can solve, I can sort of figure out what this radius is going to be. I can divide these two equations out, for example, and we see that the lift is going to drop out. So I get tangent phi, and then the mass is also going to drop out. I'm just going to do this in 2 steps and then solve for the radius. All right, so again, what I'm doing is I'm taking this equation, dividing by this equation, so the lifts cancel, the masses cancel, and then I'm just going to solve for radius. And that's just going to be v squared over g times the tangent of my bank angle. Okay, so that is my turning radius. So let's dissect this a bit. Notice it doesn't depend on the mass of the airplane, which again may be surprising at first glance. If it's heavier or lighter, that's not going to affect whether I can turn sharper or not, at least not directly. There's nothing I can do about G. All that I can really do here is I can, if I want to make a sharper turn, I need to go slower. So I'd have to decrease my stall speed if I want to be able to make sharper turns with my aircraft. So the stall speed, of course, is going to be a big thing here. The other is I can bank further, right, if I can get to a bigger angle. And if this is a passenger carrying aircraft, though, of course, there's going to be limits on that. We're not going to be very comfortable if I'm pulling big bank angles. But if I don't have passengers, I may be able to get away with more there. There's also limits there in terms of G forces, potentially, although we usually won't get that high. I'm just going to introduce this now because we'll use it later again, so it'll be good to see it a couple times. We have what's called a load factor, and that's going to be a ratio of my lift to weight. Okay, so in this case, because I'm turning, right, my lift, actually this vector here must be bigger than this, right, because only a component is going to be equal. And so my lift to weight is going to be directly, in this case for this turn, 1 over the cosine of phi, right? So as I turn further and further, I need to increase this lift bigger and bigger. And we call this, so if n was 1, if we're balanced, we would say we're at 1g. That means that I'm just feeling 1g of acceleration, or in other words, the acceleration of gravity. It just feels normal, right? If I bank more and more and I had to get the lift up high enough, so let's say I was at 2 g's, that would mean that it felt like gravity was twice as big as normal, right? I'm accelerating, my lift vector is so large that I feel like I'm being pushed down to my seat twice as hard as normal. Yeah, I feel twice as heavy, if you will. Okay, so that'd be 2 g's. And of course, that's related to this bank angle, although, for transport aircraft, we're not going to pull these high g's. But if this was like a fighter and I had to pull a really big bank angle at a steady turn, that could be one way where I'm introducing high g's. And of course, if I do a steady turn while also doing a pull-up, then I can get to really high g's. We'll talk about these load factors again a little bit when we talk about structures. But for now, just thinking about turning radius, this isn't something that we have tons of, there's a fixed range we can go to here. So from an aircraft design perspective, our main parameter that's going to help us get tighter turns is to be able to decrease that stall speed if that's something that we need to do. Okay, that's it for today. We're going to talk about some other aspects of performance related to takeoff and landing next time.